There are three factors that affect the pitch or the frequency of a stringed instrument. First thing is how long the string is. Next, how tightly is that string tensioned? And lastly, how thick that string is. If you've ever dissected a piano before, like in this picture over here, you'll notice that the bass notes tend to have strings that stretch from the top left-hand side of the piano all the way down to the bottom of where your feet are. All right, and the treble strings, they're relatively short. Next thing that may not be as obvious here, but if you ever tuned a guitar before, you'll notice that the strings usually at the top with the treble notes, they're tensioned quite high. All right, so the tensioning is a lot higher over here, and the tensioning is in general a lot looser in the lower bass end. And the last thing is that if you look closely in this picture over here, bass notes tend to be rather thick, all right, giving it more density or more mass per unit length. And on the other hand, on the far right hand side, the smaller strings, they tend to be a lot thinner. And that's also true with guitars as well. If you ever played a guitar before, you'll notice the bass note is rather thick and the treble note is rather thin. Okay, so let's go through the equation used to predict the corresponding speed of the wave as it goes through a string. All right. First thing we need to know is the linear density, and that's pretty much how much mass there is per unit length. Right. That's why it's listed as this. This letter over here is mu, which is a Greek letter, and if you were to write it out by hand, it would look something like that. Actually, you usually stretch out the left tail first, a little bit longer when you write it out. Okay, so linear density is equal to the mass of the string divided by the length of the string. Once again, always stick with mkg or mks units. All right, so mass is always measured in kilograms, and distances are measured in meters. And the next formula, which I can't really prove to you, but it works out to this. V is equal to the root of tension of the string divided by linear density. The reason why I can't prove it to you is because it does involve something known as calculus. And if you are really curious, you can just take a look at it online, and you can see the derivation of how the formula is created. All right. But what we're more interested in is the correlations here. Okay, you'll notice that with regards to the speed of the string and the tension, it's not directly related to each other. In fact, if you double the tension of the string, the speed will not double. It will only increase by 1.41 times. Right? The square root of 2 is equal to 1.41. So if you double the intensity or the tension of the string, the speed of the wave only increases by 41%. It doesn't double. You'll also notice that there's an inverse root correlation between the speed and the linear density of the string. All right. So the more dense the string is, yes, the slower it will travel. Not at an inverse correlation, but at an inverse square root correlation. So V is equal to 1 over the root of U, or more correctly, correlated. Mu means correlated. Let's go through this example here. For an acoustic guitar, which I actually measure on real life, determine the tension of the bass E string, which resonates at 82.4 hertz, and it has a mass of 5.85 grams when I measured it, and the string is physically 0.648 meters long for that 5.85 grams, okay, from the bridge to the neck of the guitar. You'll also notice that I'm giving you the wavelength here, not that you needed to know it, because you'll see that there's a correlation here, all right, that the wavelength coincidentally is double the length of the string. So the wavelength is double the length of the string itself, and I'll explain why that's true in a future episode. For now, let's just go through this question here. First thing we gotta do is, that's right, state our givens. What do we know so far? Okay. Next thing is, what are we trying to look for? Well, we're trying to look for a few things. We're trying to look for the speed of the wave, and eventually the tension on the spring. Okay, so how are we going to get through this problem over here? Well, we also got to find out the linear density. Okay, that's probably the first thing we're going to do. We're going to solve for the linear density, where the linear density is equal to the mass of the string divided by its length. Now the mass needs to be converted into kilograms, so 5.85 grams is converted into 0.00585 kilograms, and we're going to divide it by the length of the string itself, so 0.648 meters. So 0.00585 divided by 0.648 gives us 0.0090278. And if you're wondering how many digits should I show here, well, if you take a look at your givens, there are only 3 significant figures. So the minimum you should carry in your intermediate or in-between calculations should be 4. Alright, so if your givens are 3 sig fig, the minimum should be 4. I always recommend just add another digit, alright, because sometimes some heavy rounding in 4 sig fig might throw off your calculations. So I always recommend add 2 more. So if your givens are 3 sig fig, add 2 more while you're working through it. This is measured in kilograms per meter. Alright, as you can see from up here, kilograms over meters. Now that we know the linear density, we can move on to the next formula, which is V is equal to the root of Ft over mu. And we're trying to solve for the tension itself. So let's rearrange this equation first. First thing we got to do is get rid of the square root. Best way to do that is to square both sides. So V squared is equal to plus minus Ft over mu. Now there's no such thing as negative tension or negative linear density, so we're not going to worry about the negative value because it just doesn't make any sense anyways. Alright, and lastly, to isolate for Ft, we're going to multiply both sides by mu, so it's equal to mu times V squared. Now that we solve for our mu, 0.0090278 kilograms per meter by the speed of, we haven't solved for the speed yet. We can't use that formula. We need to find out speed. We know that V is equal to F lambda. Alright, frequency is at 82.4 hertz. And if you're wondering why am I using brackets, because I don't like using the x. Alright, not because I have anything against it, it's just that if you're taking physics, you're probably going to be doing some heavy math in the future. And you're going to learn by next year that this x over here does not mean multiply. It actually has a different meaning. Alright, so that's why you'll notice that secretly your math teachers have just been replacing it with a dot, because a dot is not the same thing as an x. Alright, and just to even avoid that confusion even more, we just place brackets, because you know that naturally with a bracket you're implying multiplication. Alright, I think I missed on one thing over here, which is 1.30 meters. There you go. Now I'm set to move on. So we pull out our calculator. 82.4 times 1.3 will give you 107.12 meters per second. Okay, so 107.12 meters per second squared. Pull out our calculator again. 0.0090278 times 107.12 squared gives us 103.5, what was it, 9? Yeah, 59. And this does actually work out to a measurement in newtons. Alright. I guess you have to go back to forces to figure out how the units work out, but it does work out to newtons. Alright. But that is our final answer, but we should be stating our final answer to the right precision and certainty. You'll see that in all these calculations here we're multiplying and dividing, so we should be dealing with everything in sig fig. Alright, you'll notice that all our measurements are 3 sig fig, so our final answer should also be 3 sig fig as well. So this would round to 104 newtons, and that would be the corresponding tension on one string on a guitar. And here's why I want you to start thinking about things. Alright, if you're familiar with guitars themselves, now that I'm a very good artist, there's the body of the guitar. Guitars don't just have one string, right? Most standard acoustic guitars have 1, 2, 3, 4, 5, 6 strings for a 6-string guitar, and 12-string guitar will have 12 strings. Not to say that every string is at 104 newtons, but you know that there's 6 of them. So if you're assuming that they're all roughly around 104 newtons times 6 will give you 600 newtons, which is approximately equal to 60 kilograms. So imagine you standing on the edge of your guitar. That's how much force the neck of the guitar has to sustain when it's being tensioned. Alright, it's an insane amount. And that's why if you take a look at pianos, why are pianos mad heavy? It's because they're not holding just 6 strings, they're holding a lot. Yes, there's 88 keys on a piano, and the bass notes only have 1 string. But you'll notice that the mid-range keys have 2 strings, and the treble notes have 3 strings. Alright, so it's a lot of strings, and it's under a lot of stress. And that's why you'll notice that the back of the piano is made out of cast iron. Alright, hence is the reason why pianos are so mad heavy. Okay, so there's normally a lab that we do in person. If you have a chance and you have, I don't know, a slinky around or even a skipping rope, go ahead and try out the lab on course pack page 64. Alright, I'll try to do my best with this example virtually here. There's a lovely website called PHET, P-H-E-T, and it shows strings, and let's go through a behavior of this string right now. Now, when I wobble this crescent wrench up and down, it's going to hit a hard boundary. And when it hits a hard boundary, you'll see that the wave, when it reflects back, it will reflect back upside down, because you're going from a less dense medium to a much, much more dense medium. So dense that it's a brick wall. So it's just nothing but a perfect reflection. Here we go. You guys see that? And the wrench itself is also a perfect solid dense object. So let me just decrease dampening, and you'll see that this is what ends up happening. Right? And the speed of the wave is dependent upon the medium itself. All right. So if I increase the tension, the wave will travel a lot faster. If I make it thicker, then it's going to travel slower. And what's the last one? The length will also have an impact as well, because it'll take longer for the wave to transmit and return back. All right. So this isn't a good example of a resonating string, because you'll notice that it doesn't seem to stand or appear stationary, and that's because I chose the wrong frequency for generating my wave. So I'm going to wipe this out and start all over again, and hopefully get to a decent timing of it. Oh, that's too crazy. I think I can see it now. Let's go with something like this. Whew, messy. You know what, I'm going to turn on dampening, and then just try to aim for it here. There you go. There you go. Something like that. There you go. Okay. So you'll notice that I'm able to create something known as a standing wave. You can't tell which side the energy is coming from and which side it's going to. In fact, what's really happening is that the wave's being transmitted, and as it's being reflected, it's just finishing off the wave. Because remember, the wave looks like this. So it goes up, hits the boundary, it reflects, but then it's already inverted in its transmission. So they add together, and the amplitude, you can see it doubles out. Alright, so this is a standing wave at its fundamental frequency, or at its first harmonic. And we will have a summary of this in a future episode as well. Right? So this is a resonant object at its fundamental frequency. But you might notice that while I was working for this, I could actually do some other crazy things as well. Let me just try to time it out. Like so. Yeah, that's better. Let me just drive it to saturation, and then let it dampen a little bit. There you go. Once again, this is also a standing wave. You can't tell where the source is, and you can't see where the wave is traveling. They're just interfering with each other. And now we can bring out some other important points. Alright. You'll notice that in the exact middle, it's not moving at all. Well, it's close to not moving. I tried my best as a human being to not make it move at all. Alright. And that point over there is known as a node, okay, because it doesn't appear to be moving. Now, somewhere in between it all, such as right over here, it's moving a lot. Same as right over here, and that's known as an antinode. In fact, since you can see there's 2 antinodes, this is resonating at double its fundamental frequency. Alright. It's also known as its first overtone. Let me try upgrading this a little bit more now. Alright, I'm vibrating that thing about 3 times as fast as I did before, and that's why, let me try it again. You have to get the speed just right, right? And that's why, for example, with regards to your piano, once you strike that string, it only vibrates at a particular frequency. All right, it's not going to do any other frequency other than its fundamental frequency or its overtones. There you go. That's what I wanted to generate. Okay, let's remove the dampening. And this time around, you're going to notice that there's a node over here, kind of, and there's definitely a node over here because I did a better job this time. In fact, let me just dampen it a little bit more, and I think it looks a lot better here. Okay, so this time around, it's vibrating at 3 times its frequency, and you can tell because when you look at the number of antinodes, there's an antinode over here, there's an antinode in the center, and there's an antinode about the 1/6 of the way from the right. All right, so this is vibrating at 3 times its fundamental frequency, so it's vibrating at its 3rd harmonic, also known as its 2nd overtone. Other things that we can do here is that you'll notice that on the right hand side this is a rigid object, and with rigid objects the reflected wave will always be inverted. Now if we have it as a flexible object, if I transmit a positive wave, you'll see that it returns back as a positive wave, and if I transmit it as a inverted wave, let me just dampen it more, it'll return back as an inverted wave. And if I don't want any reflection, well then I need to make sure that the medium's all matched up. So the medium over here is the same as the medium here, which is the same as the medium on the far end. So it's almost as if we were through an open window. That way we can ensure there's no reflection. And there are ways to cheat to make it seem like it's an infinite place it's going through, and we do that all the time in electronics, because even electricity behaves as a wave. Alright, so if we want to transmit a signal and we don't want any reflection, we need to match the destination, the nature of it, with regards to the transmitting medium itself. Alright. Alright, so here are a few behaviors of mechanical waves. Alright, first off, all vibrations require a medium to transfer wave energy. We're talking about mechanical waves, right? Now light is also a wave, but it's not a mechanical wave. It's an electromagnetic wave, and one of the unique properties of electromagnetic waves is that it doesn't need a medium. And that's why we can still see the sun, alright? Because again, the sunlight is blaring out lots of light, and infrared radiation and other forms of radiation as well. It goes through a whole vacuum of space for millions of kilometers, and eventually reaches the earth. Alright, so light doesn't require a medium, but sound needs a medium. If you remember my previous recording with that bell jar demonstration, the moment I remove all the air from the bell jar, you won't hear anything at all. As mentioned before, sound travels a lot faster through solids because the molecules are tightly bounded with each other. And as they're tightly bounded, the moment you shift one of the molecules, it almost instantaneously transfers the energy over to the far end. On the other hand, with gases, since the molecules are not attached with each other, they have to collide with each other, and that takes time for them to collide. And in general, the further away they are from each other, I guess the longer it'll take for it to transmit. But here's the weird thing with regards to temperature. By definition, temperature is the average kinetic energy of the molecules in motion. Right? So these molecules are all constantly moving. So as they're moving faster, then the chances of them colliding with each other is far sooner. So that's why sound technically travels faster in warmer air than in cooler air. And I'll show you a formula in the next slide for that. Alright, but for now we know that typically in solids, energy travels very quickly. And in fluids such as liquids and gases, the sound travels a lot slower. Alright, and yes, at higher temperatures, usually the rate of energy transfer does improve. Here are other key important things with regards to sound, if you weren't aware of it already. Sound travels as a longitudinal wave. So when a person shouts, they're creating this huge bubble of compressions. Now that air wants to normalize itself to standard atmospheric pressure, so for example 1.3 kilopascals. So it'll quickly expand, filling in any void. But while it expands, it knocks other adjacent molecules, causing it to compress, and then this results in a domino effect. Alright, so sound propagates as longitudinal waves. Sound, being a mechanical wave, does require a medium to transmit energy. And another interesting thing about sound is that lower frequencies typically are omnidirectional. In other words, the sound goes in all directions. You don't really need to point it at any given listener. They'll all hear it. On the other hand, with regards to higher frequencies, it is directional. So the higher the pitch is, the more you can figure out where the sound's coming from. Meanwhile, low frequency grumbles, you have no idea where the sound's coming from. And that's why if you happen to have these fancy sound systems, like 5.1 surround sound, 0.1 is for the subwoofer. And the subwoofer, you can place it anywhere in the room. It doesn't really matter because you can't tell where the sound's coming from. I mean, personally, I like placing it right behind the couch because I want to feel the grumble, right, when there's an explosion or whatnot. But other than that, it really doesn't matter where you place the subwoofer. And yes, sound can refract. It is possible. Okay, so the speed of sound in air has been determined to be at this formula here. Okay, so the speed of sound can be calculated out by this formula here. How do we get to this formula? Well, I'll show you in a future slide, but this is just the textbook formula. And let's just go through a textbook exercise first. Okay, how fast does sound travel when the air temperature is at 20 degrees Celsius? If you were to solve this as any typical word problem, start off with your givens. Your temperature is equal to 20.0 degrees Celsius, and we're just trying to solve for the speed of sound. So the speed of sound is equal to 331.4 meters per second plus 0.606 meters per second degrees Celsius times temperature. So 331.4 meters per second plus 0.606 meters per second degrees Celsius times 20.0 degrees Celsius. Hopefully you can do some mental math over here. 6 times 2 is 12, so that gives you 12 plus 331, and then that will give you 343 meters per second. Done. You want to do it the long way? By all means, do the long way. You're going to get to the same answer. Alright, as crazy as this may sound, there have been physics exams where you're not allowed to bring a calculator in, so you should try to practice without a calculator when possible. Now, different gases also have different speeds for the sound that it propagates at. Alright, the formula you see up above, that's only true with regards to regular atmospheric air, which is 80%, oh, that's too loud, which is roughly around 80%, yeah, 79% nitrogen, right? So about 80% nitrogen, 20%-ish oxygen, and then about 2% of everything else, all right? But then a demonstration that you just saw on the right, let me just run it over one more time. We're using a special type of gas. This one over here is a very heavy gas. It's sulfur hexafluoride, about 5 to 6 times more dense than regular atmospheric air. And that's why, with regards to this boat that's been filled up with regular atmospheric air, it floats on top of this very dense gas. But if you pour that very dense gas in, it's kind of like pouring water into your boat, and with enough of that dense stuff in your boat, it will sink. All right. I mean, the only reason why boats will float is because the cavity that it creates, it pushes the same amount as the water, the mass of the water. So in other words, if the boat and the person combined is 100 kilograms, it needs to push 100 kilograms of water in order for it to float. Now you know about buoyancy. Okay, now this formula here, it's something that's just shown in grade 11 high school textbooks. I don't think you ever see it again in high school. All right, and it's a fairly simplified formula. I mean, if you look at the structure of it, what you have is that you have y is equal to b plus mx. All right, so it's a simple y equals mx plus b formula. Very quick to calculate out. But in real life, it's not that type of linear problem. In fact, this is the real formula that you'll see in first year university. The speed of sound is equal to the square root of the adiabatic index of the air times the, I forgot that constant. It's the chemistry constant, the R constant. I think it's the, I can't remember, of gases. It's the standard gas constant. All right, times temperature measured in Kelvin. All right, where I may as well talk about this right now. Kelvin and degrees Celsius, their increments are exactly the same. All right, so Kelvin over here, Celsius is over here. Yeah, Kelvin's down here, Celsius up there. So if you increase by 1 degree in Kelvin, you also increase by 1 degree in Celsius. So they increase up the same. The only difference is that Kelvin starts off at 0 and Celsius has negative answers. All right, because the lowest temperature possible happens at negative 273 degrees Celsius, which they just said, you know what, if that's the lowest temperature possible, why not just reset our scale and just call it Kelvin? All right, So 0 Kelvin is equal to negative 273 degrees Celsius. So eventually when you reach 273 Kelvin, that's equal to 0 degrees Celsius. So then that's why on average they say that the average temperature of a classroom is around 300 Kelvin, because when you do the math, that's about the temperature of a classroom. What is it, 27 degrees? Something like that. Okay. Anyways, that's the actual formula that you see in the blue box here. This is the proper formula that you should be using. And once you sub everything in, you end up getting a formula that looks like this. And if you are at 0 degrees Celsius, which is 273 Kelvin, well, 273 divided by 273 gives you 1. Square root of 1 leaves you with that. That's true. All right. And for every increment that you make over here beyond 0 degrees Celsius, it does approximate to that formula. All right, remember that this is a square root formula, so technically it should look like a curve like so. But this is a y equals mx plus b formula, which looks kind of like that, right? You have your b offset right here, and then your m is your 0.606. However, if you look into this tiny little box over here, you'll notice that these two curves, they start to look the same. All right, so even though originally they do not look like the same curve, within a small region, they almost look the same. The data is on the right for that, right? At 0 degrees Celsius, they look more or less the same. And if you look at ranges that are survivable by average human conditions, you know, such as negative 60 degrees Celsius and positive 60 degrees Celsius, well, the error that's made is only roughly about 1%. It's not a big deal. And that's why in high school, use this formula and you're good to go. You don't need to worry about it. But when you're in university, realize there's a formula that's better. After all, if you end up subbing in negative 273 degrees Celsius over here, you're going to get a speed of sound that's at a number, which is impossible, because at absolute 0, all molecules stop. So in other words, all the gas in the atmosphere just fall to the ground. They don't move anymore. There's no more air for sound to transmit through. So the speed of sound should be at 0. Okay? That's just some fun information, but don't worry. This is all you need to know for high school. Okay, one last example here. If it takes an extra 5 seconds for the sound of lightning to reach the ear, then for the light to reach the eye, how far is the storm from the person? You may have heard the story about, you know, counting in steamboats, where every steamboat is, I think, about a quarter of a mile or something like that. Yeah, I think about a quarter of a mile for every steamboat. All right, so it takes 4 steamboats for the lightning to be a mile away, for example. All right. Now, we're using the metric system, so the speed of sound through air is roughly at 345 meters per second, somewhere in that ballpark. Okay, so let's figure out this problem here. There's the short way and there's the long way. I'll show you the short way first, and then you can see the long way when I just reveal it in the PowerPoint itself. Okay, the short way is by knowing that the speed of light is at 300,000,000 meters per second, compared to the speed of sound at 345 meters per second. Meaning that for time that goes by, well, that time will be far more significant for light, because 1 second, light has traveled very far. Meanwhile, in 1 second, sound hasn't traveled far at all. So in other words, this 5 seconds over here probably has the biggest influence with regards to the light itself. All right, but we don't want to calculate out 5 seconds for 3 followed by 10 to the 8, because that's just too huge of a number. So we're going to look at how it impacts the speed of sound itself. All right, because that's where we're going to really see any differences measurably. All right, so 5 extra seconds. Well, actually, we'll do the formula first. Distance, by the way, is equal to speed times time. I think we covered that in a previous episode. Or is it this one? I can't remember. Okay, speed is equal to 345 meters per second times the time of 5.0 seconds. 3 times 5 is 15. 5 times 4 is 20. 5 times 5 is 25. So 1725 meters. All right. This is all 3 sig fig. So you could just state this as 1730 meters, or simply 1.73 kilometers away. Okay, because the extra 5 seconds, you'll probably notice it with regards to the sound. Okay, so the lightning happens, boom, and it did take a certain amount of time for the light to reach your eye, but that's negligible compared to the extra 5 seconds that it took for you to be able to hear it after the fact. Okay. A different way of interpreting this, if you don't believe me on that, is to do it the long way. All right, which is the statement here. The speed of sound is whatever time it takes for the light to reach your eye plus the additional 5 seconds. So, with regards to sound, the distance we don't know yet, but we know the speed of sound at 345, and we know the sound will take an additional 5 seconds on top of the speed of light. Now, as for the distance where the light is, well, these two are going to be the same answer because you're at the same distance away from the light source. Speed of light is 3 times 10 to the 8, and we'll just leave it at t light. So we end up with 2 equations with 2 unknowns. What you're going to do? That's right, sub and solve. So you equate them together as ds is equal to dl, expand, collect like terms, and simplify, and you'll get this. 5.7 microseconds. Alright, so it took 5.7 microseconds for the light to reach your eye, and then an additional 5 more seconds for the sound of that 5.7 microseconds to eventually reach your ear. Okay, so you could sub this into this formula here and calculate it through and take a look. It's the same answer as the super shortcut. Alright, so if you ever see these type of questions in the future, it's up to you how you decide to solve it. In any case, here's your homework. Work through it diligently, and I'll catch you in the next episode.